Hey everyone, my name is Staab and today I'm going to present our paper From Principle to Practice Vertical Data Minimization for Machine Learning. This is joint work with Nikola Jovanovic, Mislav Balonovic and our advisor Martin Vetchev. All of us are from the SRI lab at ETH Zurich, Switzerland. So, what is data minimization? Well, actually the term data minimization is defined in Europe's GDPR regulation in Article 5c as the fact that personal data shall be adequate, relevant and limited to what is necessary in relation to the purposes for which it is processed. Further, the recently introduced AI Bill of Rights in the US has introduced that ML systems shall ensure that data collection conforms to reasonable expectations and that only data strictly necessary for the specific context is collected. For the purpose of this work, we note that these regulations focus directly on data collection and in particular they reflect an untrusted collector setting. Additionally, we will focus for now on the setting in which arguably most new personal data is collected, during model deployment. Lastly, as these regulations apply both widely and directly to the collection, a goal of this work is to make minimal client assumptions. So, now that we know what data minimization is, what is vertical data minimization? Take the following example of 4 users whose age gets collected. If we would minimize data horizontally, we would simply collect less data points. For example, just these two. However, while this might work for model training, it does not work for model inference. Instead, we can minimize the age attribute column vertically. For this, we replace each of the original 100 age values only by generalized values. In our case, one of 3 possible options, as you can see on the bottom right. Such generalizations directly reduce the amount of personal data collected optimally while still maintaining the accuracy in a downstream machine learning task. Now, when we look at this in a more realistic setting, for here for example on the ACS employment dataset, our original dataset on which we achieve 81.3% downstream accuracy has 196 unique field values. After our data minimization procedure, we only have 34 possible options left, significantly reducing, for example, age and education. However, the resulting downstream accuracy is only dropped by 1%. This raises 2 key questions. How can we learn such generalizations? And how should we evaluate these generalizations? This is particularly relevant as data minimization related fines have reached several million euros across several lawsuits. Existing non-adversarial vertical data minimization evaluation is at the moment significantly limited, and most existing privacy enhancing technologies focus mostly on training and or have strong client assumptions. So let us now introduce the adversarial setting for VDM in our work. Assume for this we have a list of clients, as we can see here, with 4 attributes. These clients want to get a machine learning inference by a downstream data collector. However, instead of just providing the data directly, they generalize it before sending it to the data collector. So this is how we model our untrusted data collector setting, as well as the fact that only relevant and necessary data should be collected. The downstream collector can then make an inference, in this case the classical income attribute. In difference to previous settings like privacy preserving data publishing, our VDM adversary in our adversarial setting is now actually interested in reconstructing these generalized attributes directly, as we can see on the top. When we put this into the context of most other currently used PETs, we find that while VDM does not provide guarantees during initial collection and model training phases, it is actually the only feasible inference solution in the untrusted collector setting. Further, we note that VDM here is largely orthogonal to any other PET as it directly adapts what kind of data is collected instead of modifying how data is collected. This means it can be easily combined with any other pet on the list. Putting this into a typical VDM workflow, we first start with a small set of full resolution records, here titled as ORIC. On this we train a generalization G, which produces, given such original data, a minimized version G of S-ORIC. We note that for all future adversarial scenarios, we assume that an adversary is able to observe this fully and can train on these data pairs to predict which generalized values correspond to which full resolution values. We also do this to select an appropriate generalization G. For this, we propose an adversarial evaluation step, which we will explain in more detail later in the presentation. On a high level, however, we want to select the G which has the lowest adversarial risk while still maintaining the most utility in the representation. After the generalization G has been trained, we only ever use minimized data. This means no more full resolution data is collected both during the model training nor the model deployment stage, thus complying with data minimization regulation. Now, how do we actually get to algorithms for learning such generalizations? The key goal is to find an algorithm that produces a generalization G from original full resolution data to minimized data Z. For this, we have three key requirements in this work. One, G should be global. It should be the same for all clients. Then G should be single dimensional, i.e. each attribute gets generalized individually. And lastly, G should be strict. This means it forms a strict partition of the input attribute domain, such that each value certainly gets mapped to one generalized value. With this in mind, there are obviously a few baseline options. First, we could simply split the input ranges uniformly. Otherwise, we could also apply commonly known feature selection mechanisms that are known in the machine learning community. Both of these are special cases of vertical data minimization. Additionally, there exists one prior work by Goldstein et al. Based on tree pruning algorithms that is called APT. And we also introduce another more involved baseline called iterative, which uses dynamic programming to find better generalization boundaries. However, we can actually improve significantly over these baselines in multiple ways. In a first step, we introduce neural minimizers, which use learnable neural network representations to learn generalizations that both achieve high utility and high privacy. Similar to approaches in generative adversarial networks, our adversarial minimizers have a joint objective which has one term accounting for utility and another one accounting for the corresponding privacy. This is mirrored by our mutual information minimizer that swaps the adversarial privacy objective for one that is based on mutual information. However, as we will see in our evaluation, all these methods get superseded by our privacy-aware tree, short PAT, algorithm. For this, let us take a look at the example on the right. Just as in classical tree learning algorithms, we build a decision tree with internal nodes splitting on a single attribute, in our case A. Taking a closer look at the node marked in blue, we show how we can adapt the classical Gini splitting criterion with an additional privacy term to get what we call privacy-aware Gini, or pGini for short. Inspired by fair representation learning, this privacy term in pGini intuitively states that the distribution of all personal attributes should be as uniform as possible across any split in a decision tree. Further, the parameter alpha allows us to continuously trade off privacy and utility in the resulting tree construction. To get now a generalization out of the finished tree, we simply project all decision boundaries from inner split nodes onto the attribute. In this case, we can see the decision boundaries for A would be 2 and 7. Now that we know how to build generalizations, how do we actually evaluate the adversarial privacy threat for a given generalization G? In this work, we propose 8 diverse and regulation-aligned evaluation scenarios, which are directly informed by the EU's Data Protection Working Party. We start with multiple adversaries dealing with reconstruction. In our general setting, we assume attributes to be either personal, i.e. of interest to the adversary, and depicted on the right, or non-personal, and depicted on the left. Assuming access to the minimized data C, our A1 adversary tries to reconstruct the personal attributes, as shown on the right-hand side. For this, remember that A1 could learn such a reconstruction algorithm by observing the full resolution data points used for training G. A2 builds on A1, however, only gets evaluated on predictions where they are quite certain, thus reflecting an increased focus on individuals' privacy. A3 to A5 now represent different versions of additional knowledge that an adversary might have when reconstructing personal attributes. Here, A3 assumes the adversary has access to all non-personal knowledge, as shown on the left. A4 models the worst case where the adversary has access to all but the current target attribute, and A5 depicts an intermediate case between the two. Our A6 multi-breach scenario models the case where an adversary has access to data under multiple generalizations, which for example can happen when a data collector switches their generalization after some time. Lastly, also our A7 and A8 adversaries come directly from the Working Party document. A7 models how well minimized data can be used to inform the linkage of two previously non-linked datasets, and A8 checks whether the individual entries in the minimized dataset can be singled out. Now let's look at some actual results for our A1 adversary. For this, we take a look at the Pareto curve for our A1 reconstruction adversary on the ACS employment dataset. We show classification error on the x-axis and adversarial error on the y-axis. We first identify 3 key points. On the top right-hand side, we can see fully generalized, which assumes that there is no useful data ever collected, which means that all collected data is the same. This means both the adversary and the utility inference model simply predict their statistical majority classes. No generalization at the bottom left assumes the case where no data minimization takes place, i.e. full data is always sent. This gives us an upper bound on the amount of utility we can expect to observe in this task. Optimally, we would like to be at the top left. This would mean we maintain all utility, but achieve the same reconstruction error as a majority class adversary. Putting in the Pareto curves over all methods and their hyperparameters, we can observe two things. First of all, there's a lot to be gained in the privacy utility trade-off. PET achieves almost the same utility as non-minimized data, while at the same time sacrificing only small amounts of privacy. Secondly, we notice that PET consistently dominates all other approaches in the utility privacy trade-off. This is an observation that we have made across all evaluated datasets. Moving to the A2 adversary that focuses on high certainty reconstruction, we can observe that in practice adversaries can actually make noticeably more accurate predictions on individuals where they are more certain in their predictions. For our additional knowledge adversaries A3 to A5, we find that while such knowledge helps, across all our datasets, minimization helps noticeably even in the case where all but one personal attribute is known to the adversary. With our multi-breach construction adversary, we can evaluate how well generalizations stand up under multiple breaches. As we can see below, the adversarial error of a joint breach is in some cases noticeably lower than the minimum of each individual breach. Lastly, our linkability as well as our singling out adversary give us insights about how well generalized data can be used for the more recently investigated threats of linking to initially disjoint datasets as well as uniquely identifying individual in a minimized dataset. We also include several ablations in our paper, two of which we will show here. Notably, we find that PAT, despite the joint objective, leads to strong individual attribute privacy protection. Further, we find that it is quite stable to reasonable distribution shifts as shown here on 5 dataset splits of the ACS employment dataset. In summary, we introduced a new adversarial vertical data minimization setting. Further, we provided a framework for evaluating VDM methods across various regulation-aligned metrics, and we built several state-of-the-art VDM methods with PAT ultimately outperforming all prior methods across datasets. If you have more interest in our results and further ablations, I recommend you take a look at the paper linked on the left. Thank you for your attention.